Now that we've talked about and justified the need for GPU programming and parallel programming generally on graphics processing units, utilizing the potential benefits of the massive amount of processors that a GPU gives us, let's take a look at the performance measures. Two performance measures that are important when we're evaluating our programs, because after all, our goal is to write programs that are efficient and fast. But what does fast mean, and how we can calculate and analyze the performance of our algorithms and their speeds? There are two important measures when that we should be looking at when we are attempting to analyze the speed of anything, for that matter. The concepts of latency and throughput. These are two very important measures that we will have to keep in mind when we're evaluating the performance and the efficiency of any kind of algorithm. And then there are means of calculating these measures. The idea of latency and what the latency means is the amount of time that it takes to complete one single task. Therefore, it's measured in time, and its units are basically seconds. Now, for things like operations that are happening on computers, a second is an incredibly long period of time. So we usually measure the latency in terms of milliseconds. That's 1/1000th of a second, or a microsecond. That's 1/1,000,000th of a second, or nanosecond, and so forth. Now, as you see, latency talks about time, and an alternative means of evaluating the speed and performance of a computing device, in our case, is to look at not at the amount of time that it takes for an operation to complete, but rather to look at now a fixed amount of time and see how many operations can be completed during that amount of time. And that brings the idea of throughput. Throughput is the number of operations computed in a unit of time, and we can calculate that, and its unit being number of jobs completed in time. And so usually we look at that as number of operations per second. So the two ideas of latency and throughput are related to each other, but they're actually evaluating two different measures. So if you look at the concept of time and the concept of operations, if we fix the time and calculate how many operations can be computed and completed in the fixed amount of time, this will give us the idea of throughput. And if we fix the number of operations, say one operation, and ask how much time it takes to finish that operation, that would give us the idea and the measurement of latency. So as you see, these two measures are effectively related with each other, but generally speaking, they evaluate two different standards of performance. They're aimed at evaluating two different computational standards. And usually, not all the times, these two concepts may not be satisfied at the same time. And when computations are concerned, these two measures of latency and throughput run contrary to each other, run against each other, and our goal will be to try to come up and design a common ground and a trade-off between latency and throughput. It's counterintuitive because one might say, oh well, having low latency, you finish operations faster. So how would that not be increased throughput? If you can finish one operation in short time, how can you not complete more operations in the same amount of time, in a fixed amount of time. This, if you look at a serialized process, that would make sense. If you have one serial processor, and if you give it one unit, one operation to complete, and it feeds off and sends out one completed time faster, if you give it basically two operations in a serialized manner, you expect the amount of time that it takes for them to be completed to be shorter. That makes sense. But this is not the case when we talk about parallel processing. In parallel processing, it may not be the case that if you have a processing unit that runs one operation fast, it doesn't necessarily mean that if you give it two operations in parallel, the result of completing both operations may be faster and happening over the same amount of time. So, or over a short period of time. Or if you have multiple processors working on multiple pieces of data, it may not necessarily mean that the data will be completed in a faster manner. And so we'll get into this a little bit later. So, what are the things that we're trying to accomplish and optimize when we're optimizing for latency or for throughput? To optimize for latency, we would like to minimize the amount of time that it takes to complete one task. And in traditional CPUs, it is done effectively. If you wanted to minimize the amount of time it takes to complete one task, you raise your clock speed, you make your CPUs more complex in terms of completing more complex operations, and so you will be able to optimize latency. A task comes in, and its completed task comes out in a certain period of time. If you increase your CPU clock cycle or your complexity of your CPU, a task comes in and it's going to get completed faster in a shorter period of time, and that optimizes for latency. How about throughput? To optimize for throughput, you would like to maximize the number of tasks that are completed in a certain same amount of time, and this is what is done in the graphics processing units or GPUs. What that means is that you don't necessarily want to make more complex processing units, but rather you want to have the goal of being able to synchronize and optimize your processing units in such a way that they can get more tasks done in time, as opposed to getting one task done faster than another task. So these two goals are not always aligned with each other, as I said earlier. And let's see an example about that clarifies that the two goals of optimizing for latency and optimizing for throughput may not be always the same thing. And the example is this. Let's suppose that you want to travel 10,000 miles from, say, I don't know, southwestern corner of the country to the northeastern corner, and you have two options. You can take 4 people and drive at 90 miles per hour in a car. This effectively shows us an example of what CPUs do. They can take fewer number of operations. For example, in a traditional 32-bit 8086 series of processing units, you had only one processor, and one processor can only take so many tasks to do, namely one task at a time. But it's a really, really good processor. It's designed to run that one task really, really fast. So this translates into, for example, a car taking only 4 people, like for example a quad-core CPU, and but it runs relatively fast. Its clock speed is huge, and it can take a very complex operation and finish it. So therefore, that translates into, say, a 90 miles per hour. The alternative is to take a bus that runs much slower, namely half the time, less than half the speed. So it runs at 40 miles per hour, but it can take 10 times more people. It can take 40 people. to travel them across the country. And so by solving this problem, we can actually look at the throughput and the latency of these two examples and see which one has lower latency and which one has a higher throughput. And this will show us that not always these two tasks are essentially, or these two measurements are essentially aligned with each other. So let's solve this problem. We want to calculate the latency of a car taking 4 people over 10,000 miles and the latency of a bus taking 40 people over 1,000 miles. And notice that when we calculate latency, we don't care about how many people these two cars, these two machines are transporting. We're just interested in how much time it takes to transport. When we calculate for a throughput, then we're actually interested in seeing how many people actually get transported. And that would give us the idea of throughput. Okay, to solve the problem, now let's take a look at our two cases. We have a car that is capable of taking 4 people, and then we've got a bus that's capable of taking 40 people. The car runs at the speed of 90 miles an hour, and the bus runs at the speed of 40 miles per hour. So we're interested in in calculating latency and calculating the throughput. So let's see how we calculate these two measures. Let's first take a look at latency. Latency basically means how much time it takes to complete the task. Notice here, to calculate latency, we're not really necessarily interested in how much time it takes to complete all these 4 tasks at the same time, although in case of the car, we just happened to complete all the 4 people or transport all the 4 people at the same time. But we would have calculated the same amount of time if we had just transported 1 person in the car. So the worst case scenario with the car example and having to complete 4 tasks versus 1 task is that the worst we can do is complete 1 task in a period of time. The best we could do is complete 4 tasks in a period of time. But what we are interested is in the number of time that it takes to complete our tasks here. So in this case, what we do have actually is in the case of the car, how much time it takes to transport people over the distance. And so our distance is to transport from point A to point B, and let's say that our example says that this is 10,000 miles. So that time that it takes is basically distance over speed. So in the case of the car, the distance is 10,000 miles over the speed of 90 miles per hour. So it will be 111 hours, 0.11 hours. Notice that the measure here, the unit of operation here, is in terms of hours. So car, latency of car, I don't denote that as T sub C, is 111.11 hours. In terms of my bus, the time that it takes is measured again as the distance traveled over the speed of my travel, which is essentially same distance, 10,000 miles, over now the speed of 40 miles per hour. So dividing this will give me 250 hours. So the time it took to transport across the country in a car is 110 hours almost, and the time that it takes to transport in a bus is 250. So that's almost 2.5 times longer it takes transporting 1 person with the bus and 1 person with the car. Now you see here, if we had a serialized application, if our application could complete one item at a time, if our transportation device could take and transport one person at a time, going with the car makes more sense because you get there 2.5 times faster than going with the bus. So that's completing and latency calculation. Now let's take a look at how we can go about and calculate the throughput of our applications. And I just call it THR for simplicity, because I'm lazy. I don't want to write this whole long word, throughput. So the throughput is basically the number of tasks, as we defined it, completed over a fixed period of time. So to calculate this, we need actually to calculate two concepts. First, we need the concepts of latency, or the time it takes to complete one task. So here, to complete one task, and just type 1 here. And the throughput now becomes how many tasks are computed over the period of time. So to calculate my throughput, I look at number of tasks and I multiply it by my unit of time, basically 1 second, 1 minute, 1 hour, 1 day, and then divide it by my latency, or which basically means that time it takes to complete one task. Another way to look at it is that we look and see how many operations we have that took some time to complete, and then we would be interested in how many operations we can complete in 1 unit of time. So you multiply number of tasks and then you divide them by your latency. So to do this, for the case of our car, now we're interested in latency, in throughput, right? It's basically how many people it transports over the amount of time that it transports the people, which would be the time that it transports the people. So we know that it takes 4 people to take across the country, and it takes 111 hours, 0.11 hours, so it's 4 people over these many hours. So that would give me the throughput of 0.036 people per hour. And notice my calculations in units are good because throughput is to be calculated in units of people per hour, or task per hour, or task per minute, or task per second, or whatever our time is. So for this, let's call this the throughput, and I'll call this TH sub C for my car. That's 0.036 people per hour. How about the case of the bus? The throughput of the bus basically is the number of the people it's capable of transporting over the amount of time that it takes to transport them over the country or complete the task. So it's capable of transporting 40 people over 250 hours, and again its unit is going to be people per hour. So it's going to be 0.16 people per hour. So the throughput TH sub B for bus is going to be 0.16 people per hour. So for the car, my throughput is 0.036, and for the bus, it is 0.16. Notice that the latency of the car is almost 2.5 times more or better than the latency of the bus, but the throughput of the bus is almost 4 times better, 4.5 times better than the throughput of the car. Now, this is the big question. This is the big paradigm here that we are interested in answering. Now, should we go with the car or should we go with the bus? If you're interested in completing an operation in shorter period of time, if your application's interest is the time of completion, regardless of the operations that you have, then you want to optimize for latency, and that's what CPU design is. You want faster and faster CPUs. But when you bring into the mix now the number of operations that are to be completed, then the throughput is a question that you may be more interested in, because you may end up with a design that is slower per operation, but putting in the mix that now you can do more operations, then overall completion of all the operations may be done in a shorter period of time, meaning you would end up with completing more tasks in a given time. And that is the idea behind throughput. So here's the design paradigm of GPU design. We want to create an architecture that optimizes for throughput. And to do so, we bring in a large number of simple compute units. And essentially, what that means is that by increasing the number of compute units we have, we basically are aiming to increase the number of operations that can be completed over a fixed period of time, because now we have more compute units. In order for us to be able to do this, to bring the large number of simple compute units, they need to be simple compute units, which means that programming these compute units is going to be more restrictive. We cannot do massive complex operations on them, rather very, very simplified operations. And then we utilize a parallel programming model. We must utilize a large number of these processing units to be able to accomplish our task, because our task is twofold now. We want a large number of process units that are simple, so they can't really do massive things on their own. But what we want to do is that we want to get them busy at all times. We want to make all these processing units to work all the time, so that we will be able to accomplish many, many more tasks in a given time with these number of processing units that we have. So again, our goal would become optimization for throughput. The latency of a single computation with this model may be longer. Notice that our process units, our simple compute units, are simple compute units, which means that to compute a complex operation, they may need to take, and they will need to take, longer time to compute. But if we can keep all these processing units busy, if we can design our program in such a way that it controls these units, it synchronizes and works with them together, basically that process coordination that we talked about earlier, and in such a way that larger number of tasks can be done in the same amount of time, then we will be able to increase the throughput of our calculation. This is the same thing that we just noticed earlier in calculating the latency throughput of the car and the bus. If we have one person to transport, and if we transport that person with the bus, essentially what we're not utilizing is the empty seats on the bus. Same logic applies. If you cannot utilize all of your processing cores on your GPU and keep them all busy, you would end up with a low latency, which essentially translates into low throughput. So we're not going to essentially work and benefit from our GPU calculation. So going with a faster unit and putting it on the CPU makes sense. When you have a large number of people to transport, although going by car may mean getting there sooner, but then that car needs to go back and forth, which means that it can transport much less number of people compared to the transportation speed throughput of a public transportation system like a bus. So this will this is our idea. This is the big idea here in terms of GPUs. And why is it important for us? Why is it really an incredibly important thing to notice? And this is probably the motivational slide. This is the motivational speech that I'm giving now, is that now we're in the big data era. And we know that our computation has reached the limit. We know that we cannot make CPUs any more faster than they are. In terms of computational speeds that we have seen so far, we may be able to see the speeds doubling, but we're not going to in any time soon get into petahertz scale. On the other hand, we are in the era that there is a massive amount of data out there that we can process them, and we have the computational power to be able to do so. We just don't have the time to do it. And if you look at visualization applications, simulation applications, data mining and data warehousing, a lot of big chunks of data that are out there, and if we can shift our view of serialized processing of one piece of data at a time to this massively parallel processing paradigm, then we will be able to accomplish a lot. And this is the time to do so. And we are the ones who can actually bring about this massive shift, or be a part of this massive shift, optimizing for throughput, utilizing GPU programming, general purpose GPU programming for massive calculations. CUDA essentially talks about and introduced the idea of heterogeneous processing. And this is probably single most significant factor in terms of our design. And I'll talk about this heterogeneous programming next in our journey to understanding CUDA.